In this video, we're just going to look at a very big picture overview of how you handle confidence intervals and hypothesis tests, the slight differences, whether you're dealing with one proportion or one mean. Okay, that's what we're looking at here. All right, so let's take a look then at confidence intervals first. So for a yes-no trait, right, versus a numerical trait, here you measure yes-no trait with a proportion. So your formula is p hat plus or minus z times standard error in p hat, right? And remember that the way you found standard error is standard deviation of p hat was square root of p times 1 minus p over n. But since you were trying to estimate p, you didn't know p, you used p hat, right, in the place of p. So we found that standard error was square root of p hat, 1 minus p hat over n, right? So use that p here and here. You estimate both of these with sample proportion. So what happens with a numerical trait? Well, with a numerical trait, your sample estimate is a sample mean, and then you add or subtract a t multiplier instead of a z multiplier times the standard error of y bar. All right? So now here in the standard error, the standard deviation of y bar is sigma over square root of n, where sigma is the standard deviation of the population. Well, rarely do we know that. I mean, there's some kind of uncommon cases. So, for example, maybe at a college might know, for example, the age of every student, so it would know that data for everybody in the population. But that's very unusual. You rarely know the standard deviation of the population. So what do? We approximate the standard deviation of the population with the standard deviation of the sample. So this is the standard deviation of the sample. And remember, that is that formula that we did, square root of the sum of y minus y bar squared over n minus 1. That's that formula. So that's what S is. Now, as far as z and t, so the z multiplier and t multiplier both come from this t multiplier sheet, and the z multiplier is actually over here, degrees of freedom of infinity. There's your z multipliers. For the t multipliers, you have to just take sample size and subtract 1. You find out your degrees of freedom and whatever confidence level, and you find your t multiplier. So that's the big overview for confidence intervals. And for hypothesis tests, okay, for a yes-no trait versus a numerical trait, all right, you would write for the null versus the alternative, p equal to a percent, because again you're measuring yes-no trait with a proportion. Then you'd say p is either greater than, less than, or not equal to that same percent. Well, with a numerical trait, what you'll be doing is saying mu equals a number, right? Or mu is greater than, less than, or not equal to that same number, because we're looking at a numerical trait, and so an average is what measures a numerical trait. Now, with conditions, there's another video that goes into this in more detail, and if you look at the comparison of the conditions for a yes-no trait versus a numerical trait, we went over this. So the independence is the same for both the yes-no trait and the numerical trait. The outcome of one trait won't affect the outcome of another. Randomization, the fact that every person or object has an equal chance of being selected, is the same for both the yes-no trait and numerical trait. 10% rule, that the sample size is less than 10% of the population, is the same for the yes-no as it is for the numerical trait. This is where they differ. In establishing the representative sample, for the yes-no trait, needed to show at least 10 people or objects with the trait and 10 people or objects without the trait in the samples. So we found that by np greater than or equal to 10, n times quantity 1 minus p greater than or equal to 10. Now for the numerical trait, and there is a video on this, so you might want to go check that out, you would have to say, well, what's the sample size that I have? If I have a sample size greater than or equal to 30, central limit theorem applies, and there is a video on this. And if the sample size is less than 30, then I either have to be told the population is normal, or I have to show, using whatever data I'm given, that the sample is approximately normal. Again, there's a video on this, right? So that's how the conditions are different. And then, so it's only through representative sample. All right, so here, representative sample is what's really different. The rest is all the same. And then when you go to make your distribution, you have the mean is p. Here, the mean is mu. And now here you do use standard deviation, not error. The reason is you're assuming that this p, right, is true until proven otherwise, and so you can use it. So actually this is the case you can use the standard deviation. With the numerical trait, you have to use standard error because you don't know sigma. So you have to use s over square root of n. Okay? And then when you find your z-score, you use p hat. How far is that from p over the standard deviation of p hat? Here you're going to use t-score. How far is my sample mean from mu over the standard error of y bar? And then you're going to use here NCDF from one z-score to another z-score. And this will give you your p-value. Whereas here you're going to use TCDF from one t-score to another t-score. And then another big difference here is degrees of freedom. Right? And this also gives you your p-value. Okay. But once you have your p-value, then they're the same again, because really you compare it to the significance level alpha, and if the p-value is less than alpha, you reject the null. Say there's strong evidence for the alternative. If the p-value is greater than alpha, you do not reject the null, and you say there's not enough evidence for the alternative. All right? So that's a general overview. Thanks so much for listening.